Good afternoon. So this is our lecture number 31st. In the previous lecture we discussed about measurement of velocity. Now there is one more important parameter in multi-phase flows, that is actually surface tension. Okay. So surface tension comes under the properties of the fluid mediums which are participating. For example, earlier parameters which we have talked about, void fraction and velocity, these were nothing but the flow parameters. So other than that, pressure and temperature also are important parameters, and typically the measurements of pressure and temperature are identical to the ones which we do for single phase flow. So that's why I am not taking that topic separately. At the same point of time, whenever we have to do the measurement of the properties, we have three important properties. One is density, second is viscosity, and third is surface tension. And if heat transfer is also involved, then few more properties also comes into picture, such as thermal conductivity and specific heat, etc. Okay, so the measurement of thermal conductivity and specific heat, as well as the density and viscosity, is something which we do study in our undergraduate courses as well. So that's why I am not taking that part separately over here. So if you want, you can quickly revisit your undergraduate courses, particularly say fluid mechanics, for knowing the measurement principles for density and viscosity, and typically applications of heat transfer for measurement of thermal conductivity and specific heat. Okay. Over here, we will quickly try to see the measurement of surface tension. This is also important from the perspective that density, viscosity, thermal conductivity, specific heat, etc. are the standard, considered to be the standard properties which are inherently property of a particular fluid. So that's why majority of the fluid suppliers, commercial suppliers, whenever they sell their fluids, they also provide the details of all these properties. But typically, the interaction of one particular type of fluid with other types of fluids depends upon the requirement of the application, and that is not standard for the fluid suppliers. So majority of the time it becomes important for application users or end users of the fluids to measure the surface tension or interfacial tension of the fluid mediums, because that will be depending upon the pair of the fluids which we are using. Okay, so surface tension is not a property which is identical or fixed for a particular fluid. That depends upon the pair of the fluid. For example, if you consider water, water in presence of say air will be having surface tension of 0.072 Newton per meter. Okay, but if you put water in the presence of some other surrounding fluid, say kerosene oil, mustard oil, etc., then value of the surface tension, or in other words interfacial tension, will be actually changing. So surface tension typically we use the term when we are measuring the tension of a liquid in presence of air. Okay, but when we do measure the interfacial, when we do measure the tension at the interface between the two liquids or other fluids, then we call the term interfacial tension. Okay, so there is one key difference between surface tension and interfacial tension. What is that? That we will try to see in this particular lecture, and also we will try to see some of the measurement techniques for surface tension, and then at the end we will talk about uncertainty analysis. Okay, so we all know about surface tension. So say this is nothing but a pool of water. So we know that if I have some set of molecules over here, then the interaction forces will be identical in all the directions, but the molecules which are lying at the interface, their interaction forces will not be identical, because of which these will be actually subjected to tension. Or in other words, I can say that the molecules which are at this point, these are not in equilibrium. Okay, so these molecules has to do, these will be having some pulling force in downward direction. So if this molecule has to come down, then of course one molecule from the core has to go there in order to maintain the same volume of the fluid, okay, and maintain this free surface. So because of which always due to the molecular motions, we will be finding that some energy is being invested in order to bring this molecule to the free surface. Or in other words, if you have to increase the interfacial area, okay, so say if instead of this I want to bring tank wall to this side. So if I bring tank wall to this side, then this much interfacial area I am increasing. So if I have to increase this much interfacial area, so some additional molecules from the core I have to move to this free surface. So in order to increase this area, I have to invest certain amount of energy in order to bring the molecules from the core to the free surface. Okay, so that energy is typically we call as nothing but surface tension. Okay, so surface tension can be actually defined in multiple ways. So one so typically the two standard ways are chosen. One is the concept based on energy and second is concept based on the force. So in terms of energy, you can consider, say you have some liquid element. Okay, so this was the liquid element. Now what you have done, you have say broken this liquid element through this plane in two halves. So once you have broken this into two parts, so you have got one interface and you have got this second interface. So in order to create these two interfaces, while you are breaking this liquid column into two interfaces, you have to invest certain amount of energy. So say EC is the cohesion energy per unit area. What I am saying, EC is nothing but cohesion energy per unit area. Okay. On unit area, why I am talking about cohesion energy? Because I was having the cohesive forces, because this liquid element is of same type. So when I am breaking this, at this interface earlier there was cohesion between the molecules, because of which it was actually staying as an intact liquid element. But once I have broken it, I have worked against the cohesive forces, so that's why it has created the two interfaces. Okay, so from this concept I have now, so this area I have actually divided into two portions. So that's why I can write that cohesion energy can be written in terms of 2 into sigma L. Okay, because cohesion energy I am writing as energy per unit area. Okay. Now similarly, if you all know in your basic fluid mechanics, we do this thing that if we have say a three wall rigid three wall system, and then if in this system we have one movable wall, okay, and that movable wall is actually, and in this system we are holding a liquid film, then ultimately what happens, if you keep this and you don't apply any force, then what will be happening, this will be derived towards the left side. So in order to maintain this at its position, we have to apply certain amount of force F, and amount of this force F will be equal to value of interfacial tension into, say L is length. So one interface will be on top side, other interface will be on bottom side. So I can write F is sigma 1 into 2L. Okay, so in terms of force also, it can be written as force per unit length. Okay, so this is the basic idea of surface tension. So whenever we are considering the interactions or interfaces are created by destroying the same type of molecules, it means by working against the cohesive forces, then typically we call the term as surface tension. Okay, and surface tension is something which is a strong function of temperature. So you can see there are different equations which gives the dependence of the temperature on the surface tension. So here you can see this Ivos equation. This tells that sigma 1 into V power 2 by 3 equal to C times Tc minus T, where Tc is nothing but critical temperature. Okay, so when a liquid reaches at its critical temperature, corresponding to that this T will be equal to Tc, and ultimately the value of surface tension will be equal to 0. So you can consider that if you have the like molecules, okay, throughout present, then there will not be any interface. If you are not having any interface, in that case your value of surface tension will become 0. Okay, so V is typically called as molar volume in meter cube. C is a constant, and for many liquids the value of this constant is 2.1 into 10 to power minus 4 joule per Kelvin. Then we have also another equation, van der Waals equation, according to which sigma L can be written in terms of sigma naught into 1 minus T by Tc power n, and typically sigma naught is a constant value for a particular type of liquid, and n is equal to 11 by 9 for many organic liquids. So this is how, by using these relations, actually you can calculate the temperature dependence of surface tension. Okay. One another important parameter we have been talking about long when we discussed the hydrodynamics of bubbles and drops. Okay, we studied that if we are having some impurity at the interface, that impurity will be actually altering the value of surface tension, and because of that alteration in the surface tension, the internal circulation patterns of the bubbles and drops changes, and that changes the overall hydrodynamics. Okay, so how impurity alters the surface tension, that also actually we can quantify. So let's consider that our we are saying our main solution as liquid, and then in that liquid if we add some substance, so that substance we are calling as solute. So how solute concentration is actually changing the surface tension, that is something which we can see over here. So here you can see that in a solution I have added NaCl at different weight levels. Okay, and here you can see when I have added the NaCl, there is no change in the value of the surface tension. On contrary, if I add propanol into the solution, then upon addition of propanol into the solution, you can see the surface tension is actually decreasing. Okay, so what is the reason for that? The reason is NaCl is nothing but an electrolyte. So electrolyte prefers to be in the bulk rather than in the surface. So when you add an electrolyte, say if you add NaCl in water, it will be mixing with the bulk of the liquid. So once it is mixing with the bulk of the liquid, its molecules will not concentrate on the free surface. So if these are not concentrating on the free surface, in that case our surface tension will not be changing. On contrary, if you mix an organic solute, organic solutes are typically having hydrophobic behavior. Okay, so certain molecules in organic solutes, these have actually hydrophobic behavior. So because of the hydrophobic behavior, these will not be mixing in the bulk of the solvent, but these will be concentrating on the interface. So once these are concentrating on the interface, then we will be seeing a decrease in surface tension. Okay. So typically when organic molecule has polar part together with the dominant hydrophobic part. So do you know what do we mean by polar part in any molecule? Polarity means charge. So typically, say if you have some molecule such as CO2, okay. So in case of CO2, what happens? Oxygen is more electronegative, so it will try to pull a electron pair, because of which some permanent negative charge will appear on this and a permanent positive charge will appear on this. Okay, so this type of molecules have actually, these are called as polar molecules. Okay, so which have permanent charge, and so this polarity of the molecule is one source of the surface tension. Second source of the surface tension is dispersive component. So dispersive component is in your molecules or atoms, many times there is fluctuation of charge. So sometimes there will be one charge and sometimes charge will be actually vanishing and it will be becoming a neutral. Okay, so that type of fluctuations within the atom or molecule leads to dispersive contribution in surface tension. So overall surface tension comes because of the dispersive component and the polar component. So typically if I have an organic molecule that has polar part and hydrophobic part, then we will be finding that solubility in the bulk is small and molecule tend to absorb mostly at the surface, which will be causing the decrease in surface tension. Okay, so such amphiphilic molecules are referred to as surface active agents or surfactants. So the solutes or the solutions which decreases the surface tension, these are called as surfactants. Okay. So this is one simple solution given over here, cetyl trimethyl ammonium bromide in phosphate buffer solution. So for its different weight percentage, you can see how much there is decrease in the surface tension, and after this point it becomes almost stationary, and you can see the weight percentage is of the order of 10 to power minus 6 or 10 to power minus 2. So it means that these type of molecules which are too much hydrophobic and polar, these will be leading to significant decrease in the value of the surface tension, okay, upon very small addition of their concentration. Okay, now comes the next concept, which is interfacial tension. So in case of interfacial tension, we can assume that, say, I have two fluids which are resting. This is fluid 1, this is fluid 2. So when I have this type of combination, fluid 1 and fluid 2, in this case, of course, this was the interface. At this interface, what is there? Now these will be having nothing but different types of molecules. So in between these different types of molecules, we will be having adhesion. Okay, and ultimately, say this sigma AB is the interfacial interaction term over here. Okay, so if I now break this interface into two parts, so one will be interface of fluid 1 in the presence of air, second will be interface of fluid 2 in the presence of air. So here one interfacial one surface tension I will get sigma A, other surface tension I will get sigma B. Okay, so what I was having initially, I was having interfacial tension sigma AB. On this interfacial tension, what I have done, I have added certain amount of energy which is equal to energy of adhesion. Once I have added that energy, that has led to creation of two new surfaces having surface tension sigma A and sigma B. So that I can write in terms of sigma A plus sigma B if all the quantities are written on per unit area basis. Okay. No, this is, we are not considering at the same point, we are considering at the interface, but above that point we have one type of fluid, below that point we have other type of fluid molecules. So that is, what is the friction? Friction is because of the interfacial force, okay, or interfacial shear. Here you are not talking about any shear force. Here you are considering the forces which are coming because of the nature of the molecules. Okay, so I told you that surface tension is what because of which phenomenon? Either because of dispersive or polar components. So that depend upon the nature of the molecules. Okay, so that is a molecular level force. So once it is arising because of the nature of the molecule, so in fluid 2 you have different type of molecule, in fluid 1 you have different type of molecule. So because of which their surface tension will be actually different. Okay, is this point clear? So again it means that if you have to calculate interfacial tension between two fluids, then first you should know their individual surface tensions. It is very easy to determine the values of individual surface tensions, but along with that you also know the adhesion energy between these two fluids, and determination of value of adhesion energy is something which is not straightforward. So typically the value of this adhesion energy is empirically given, and these empirical relations are mainly as functions of sigma A and sigma B. Is this point clear? In order to calculate the value of surface tension, you should know first the values, interfacial tension between two fluids. You have to first know the values of surface tensions, and you also have to know the value of adhesion energy. Okay, and typically adhesion energy is something which you can calculate from empirical relations in terms of functional dependence of sigma A and sigma B. Okay, but we will not be doing this thing because we will try to see certain methods experimentally which can give you the value of surface tension as well as the interfacial tension directly from the experimental measurement. Okay, so let's try to see certain methods. So the methods which can be employed for measurement of surface or interfacial tension, these can be majorly categorized into two types. One are forced based methods and second are drop shape based methods. So force methods include drop weight, ring method and Wilhelmy plate method. And then based on the drop shape, we have pendant drop shape, then rotating cylinder method and maximum bubble pressure method. Okay, so by using these methods we can experimentally measure the value of the surface tension. So this is the first method, which is drop weight method. So in case of drop weight method, what you will be doing, this is your liquid, this liquid you are passing through a needle. Okay, so in this needle, if you assume that the flow in the needle is inertia free, it means you are not pumping the fluid. Fluid is coming because of its own weight and it is having very extremely small velocity. Okay, so because of this, what will be happening, at the end of the needle you will be finding there is formation of a drop. So typically when you close a tap, what happens? At the end you find that some drop is actually stuck to the surface of the tap, and after some time, once it grows in size, then it actually drops down. But typically the size of the tap is actually large, so drop will be having other interface oscillations also because of the presence of surrounding air. But if we are not considering that much large size, if I consider my needle to be of say 2 mm or 3 mm diameter, so in that very small needle, whatever the drop that will be attaching to the needle surface, its size will be so small that if any randomness is there in the stagnant air, that will not be leading to much interface oscillations. Okay, so here you will be finding a spherical kind of drop will start appearing, and we know that if this drop is hanging from a surface, this is nothing but a pendant drop. Okay, so now if you see what are the forces which are responsible for hanging of this drop, this drop is touching the outer periphery of the needle and immediately outside that there is air. Okay, so it means at the periphery of the needle some surface tension force is there which is actually holding the drop against its weight. Okay, so that is the thing. Here you can see, if you consider the shape of the drop, so from the top it will be looking something like this because this is the needle diameter. Okay, so at the needle diameter, particularly at the periphery of the needle, there will be this surface tension force in upward direction, and the value of the surface tension force will be sigma L times 2 pi r. Sigma L times 2 pi r, and the force which is acting in downward direction is, that is WD, because once this weight will become just equal to the surface tension, immediately just become equal to the surface tension force, immediately after that you will be finding there is weight has become slightly higher than surface tension. What will happen? Drop will fall. Okay, so if I can measure the weight of the drop, so if I keep this entire setup on some weight measurement device, okay, and if the least count of that weight measurement device is such that it can measure the micrograms weights which will be of that particular drop, so in that case you will be finding, by knowing this weight and then equating to this equation, you can calculate the value of surface tension. Now here this Fw we are using, so Fw is nothing but a correction factor, okay, and this correction factor is function of radius of the needle. This is function of radius of the needle and volume of the drop. So typically you can see the correction factor is when radius of the needle is equal to 0, corresponding to that it is 1. As you increase the radius by volume ratio, then value of correction factor actually decreases. Okay. So if you are using this liquid in presence of surrounding air, it will be giving you value of surface tension. If you are allowing this liquid to fall in presence of any other fluid, typically this fluid has to be of low density. Okay, so if you allow to fall in this liquid, then you will be finding, in that case you will be having nothing but interfacial tension. Okay, and at the same point of time, in first case what we are doing, we are not including here buoyancy force, considering that air is having very less density, so it will be almost negligible. Okay, but in this case here size is also very small, so because of that it is negligible. But if your densities are close to each other, in that case you may have to include that correction because of the buoyancy force as well. Okay, is this one clear? So this is called as drop weight method. So very easy method, you can simply by just recording the weight of the drop, you can actually calculate the value of the surface tension. Okay.
सर इंटरफेशियल में जो हम सब डालेंगे जिसका चेक कर रहे हैं उसकी विस्कोसिटी ज़्यादा होनी चाहिए ना?
No, viscosity can be whatever, that we are not considering, because viscosity will be influencing only if we are considering the relative motion between the phases, but we are not at all interested about relative motion. Okay.
तो सर वो फ्लूइड के अंदर जाएगा कैसे?
सर उस फ्लूइड की डेंसिटी ज्यादा होगी, वो नीचे क्यों गिरेगा?
Whose density?
तो जिस फ्लूइड जो फ्लूइड है, इसका डेंसिटी अगर आप लिक्विड ड्रॉप से ज्यादा है,
The fluid whose density, the fluid whose interfacial tension we are measuring, its density is high. Okay, it is a high density. But the fluid in whose surroundings we are measuring the interfacial tension, that has to be of low density. Okay, is this one clear? All are clear with this idea? Say you have to measure the interfacial tension between water and kerosene. You cannot put kerosene inside the needle and water over here. Okay, in that case what will be happening? Kerosene is a low density, so this drop will not fall, it will always be lifted because of the buoyancy force. But if you do the reverse combination, so if you inject water through the needle and then keep kerosene in the surroundings, in that case you will be able to do this. Okay, so that is how you have to actually select the combination. Is this one clear? The next is ring method. So ring method means, despite of using, so here what you will be doing, you will be using a circular ring. Okay, and this circular ring you will be first dipping into the fluid, and after that you will be slowly raising this ring in upward direction. Okay, while you are raising this ring in upward direction, you have to record the force, how much force you are applying to pull the ring in upward direction. Okay, so at one instant you will be finding that your interface is having this shape. Okay, so interface is having this particular shape. So corresponding to that instant, if say Fr is the amount of force which we are applying on the ring, then Fr will be equal to weight of the ring, okay, plus surface tension force which is acting. So now can you tell me what will be surface tension force?
अंदर वाला जो है सर वो पैरामीटर अंदर वाला बाहर वाला
Yes.
So
So
R1 2 pi R2 लेकिन एवरेज लेंथ का साइज है
say yes. So say if this is my cross section of the ring, okay, so the mean radius of ring cross section is capital R, and the radius of the ring cross section is R, and this is capital R. Is this point clear? All are clear with this idea? So this is my ring. If I take a section of the ring, so section of the ring will be looking something like this. So the radius of the ring with reference to its center, mean radius of the ring is capital RR, and the cross-sectional radius of the ring is actually small rr. Okay, is this point clear? Now you can see that ring 1 is outer surface of the ring is touched by the fluid. So it means pi rr into sigma LF. One is from outer side, other is from inner side. So that's why 2 it is becoming 4. Is this point clear? All are clear with this? So when you have a ring, here you can see how this ring is holding the fluid. One is in the outer side of the cross section, other is inner side of the cross section. So outer side of the cross section, if you consider mean radius to be RR, then 2 pi R into sigma, and second 2 pi R into sigma for other side. So that will be giving you this 4 pi RR, and here again FR is the correction factor, and value of this FR will be function of RR by VR 1 by 3 and RR by capital RR by small rr. So it means it will be function of the size of the ring divided by its radius. Okay. Then third is Wilhelmy plate method. So in Wilhelmy plate method, what we will be doing, instead of a ring, we will be using a plate. Okay. So this type of plate in 3-dimensional plane, you will be finding it is having some width also. Okay. So in this case, if you see this portion is actually wetted by, so this entire portion will be wetted by the fluid. So here you can see if PP is perimeter of the plate, then PP times sigma LF plus weight of the plate will be equal to FP. Okay, where FP is the amount of force which you are applying in upward direction in order to pull the plate. So in all these methods, you have to use some transducers and some arrangement which can pull the plate. At the same point of time, it can also measure how much force actually you are applying. Okay, so that type of automation you have to do. Okay. Then comes the method which is based on the shape of the drop. Here, if you want to include, that will again depend upon the density of the plate. If density of the plate is say weight of the plate is too large in comparison to amount of fluid displaced, then buoyancy will not come. So in majority of these cases, weight of the ring, weight of the plate, these are so high that that displacement of fluid actually can be neglected. Okay. Then comes drop shape method. In drop shape method, what we can do, of course, whatever I am presenting over here, this is the final empirical relation. There is theory behind that. That particular I am not explaining you over here. I am just directly explaining the process by which actually you can measure the surface tension. Okay. So if you allow drop to hang from the needle, and if you take the photograph just before its pinch off, once the drop is just about to leave the needle, if just before that you take its image, and if you fit that image using image analysis, if you fit this bottom portion of the image, so here you have see all these blue colored points are nothing but fitted data points which are tangent to the interface of this image. Using image analysis you have fitted, and then Using these points, you have fitted a red circle over here. Okay. So if you fit this, then you will be able to measure different parameters. One is this particular parameter, which is called as equivalent diameter of this. Okay. And half of this equivalent diameter will be your R naught. Now, if you from this point, if you go DE, means in this circle, then whatever the diameter you are having at this point, that is called as ds. Okay, so using this ds and de, we can measure one factor beta. Beta is nothing but using this function, it is a function of ds by de and its powers. Okay, once you have calculated beta, then we know that for a bubble, surface value of beta can be written in terms of delta rho g r naught square by gamma. So this comes from some theoretical analysis. That part actually I have skipped over here. So I am just directly giving you the relation. Okay. So from theoretical analysis of this shape of the drop and force balance, you can calculate that beta will be becoming delta rho g r naught square by gamma. So here you know the density difference between the two fluids, you know gravity, you know r naught, and if you using this relation you calculate beta, then you can calculate the value of gamma. So this is called as drop shape method. You have to simply capture the shape of the drop which is hanging from a needle, and using the image analysis, if you can determine these parameters dE, ds and r naught, you can actually calculate the value of the surface tension. Okay, and one important point is given over here. So here radius of curvature is given in pixels, and here you have taken the number of points. It means how many number of points you are taking to fit this circle. So if you take very less number of points, then your estimation of radius of curvature will be actually too much oscillating. When you increase the number of points, if you have good number of points to form this circle, then actually you will be getting almost a steady value of the radius. Okay, so it means the accuracy of this method depends upon the accuracy of the fit of this circle, how many data points you are using from image analysis to fit this circle. Is this one clear? Next method is rotating cylinder method. So rotating cylinder method is typically used when we want to measure the surface tensions which have very small value. If you have very small value of the surface tension that you want to measure, then majority of the other methods may not work, because if surface tension is small, then instead of coming as a pendant drop, your fluid may come out as a continuous jet out of the tube, etc. Okay, so when you have very low value of the very small value of the surface tension, in that scenario you can use this method. So you can take a small capillary tube kind of thing and you can rotate it. Okay, so once you will be rotating it, then it will be, so you have two fluids over here. One is, this one is bubble of the fluid whose surface tension you want to measure, and outside you will be having some other fluid. Okay, so when you will be rotating this, you will be finding that you will be getting some elliptical shape of the bubble. If you take the photograph of this elliptical shape of the bubble, means you are considering a transparent tube. Okay, then you can measure the maximum radius of this, that is RB. So surface tension is nearly equal to omega square into delta rho RB cube by 4. Okay, so using this method you can calculate the surface tension, particularly the small values of the surface tension. So typically when you use two different liquids, in that scenario the value of surface tension is actually small. So if you use some liquid with a gas pair, then value of surface tension is higher, but when you use liquid pairs, then interfacial tension values are small. So typically for liquid pairs, this type of method is actually employed. Then this is the fourth method, the next method, which is maximum bubble pressure method. Okay, so maximum bubble pressure method is based on very simple characteristic of the bubble, and characteristic of the bubble is that if you plot radius of curvature of the bubble with its volume, you will be finding that, say, these ABCD nothing but represents the different time instants of the bubble growth out of a needle. So A is when bubble has just started or the drop has just started appearing at the needle. So at this point, if you fit a circle, so radius of this will be large. So you have large radius at A point. But when you are shifting from A to V, the value of radius has started decreasing. So value of radius is decreasing, but once you reach point C, at point C, you have drop which is just completely fitting a circle within the needle. Okay, which is fitting a circle completely within the needle. And after this point again, if you go further, then value of radius has started increasing. So it means that you will be getting radius versus drop volume curve, something like this. Okay, so corresponding to the point where drop radius is identical to radius of the needle, corresponding to that you have the lower value. So this is nothing but RC. Okay, is this point clear? Now you can employ this principle to determine the surface tension. We know that within this bubble and outside the bubble, whatever pressure we have, delta P will be inversely proportional to R. Delta P will be inversely proportional to R. So it means that when my radius is smallest, corresponding to that I will be having the highest pressure. Okay, and when radius is large, then value of pressure will decrease. So what I can do, I can have an arrangement something like this, that this is my tube. In this tube, I have dipped this tube in some fluid whose surface tension I want to measure. Okay, and then in this fluid I have started pumping air from the backside, and the air flow rate of this air is actually extremely small. I have to keep so that inertia of the air does not affect the shape of the bubble. Okay, so I have to say flow air in terms of microliters per second flow rate. So if I do that, and then this air line I also connect to a pressure transducer, then what I can do, I can record the value of pressure as function of time. Okay, so initially my pressure will be lowest, then it will keep on increasing. At some point it will be highest, and then again it will start decreasing. The instant at which I am having highest value of the pressure, delta P max, that point will be corresponding to radius when radius of curvature of the bubble is equal to the radius of the needle. So that is what I can do. So I can write sigma L equal to delta P max into RC by 2. Okay, is this point clear? From where this is coming, that I think you should be able to appreciate now. For a bubble, Laplacian pressure drop is nothing but equal to 2 sigma by R. Okay, so that is what I have written over here. Is this point clear? So this is another method which is based on the pressure measurement in the bubble, and how this pressure measurement actually can be employed for calculation of the surface tension or interfacial tension. Okay. Now let's come to next part, which is uncertainty analysis. Okay, so typically when we talk about uncertainty, we have to consider that our measurements, whatever experimental measurements we are doing, these are not always 100% accurate. Okay, so before going to the uncertainty is something which is coming because of the random fluctuations. Okay, but before going to uncertainty, we have to, while we are doing the experimental measurements, we have to understand that what kind of mistakes we can do while we are doing the experimental measurement. Say one mistake can be, you are using some pressure transducer, but you have not connected it to the required power source. Okay, you have started doing the experiment and some random noise is coming and just you are assuming that only as your output. Okay, so that you have some loose connection somewhere, you are not getting actual value, but noise only you are considering, say, your data point. So that type of error is called as gross blunder. Okay, so gross blunders have no meaning actually. Whatever data you are obtaining while gross blunder is there, then that is having no meaning. Second type of error can come is that your instrument is having some bias. For example, if you are using a Bourdon tube pressure gauge for long duration. So typically in Bourdon tube pressure gauge, what is the principle? There is some stiffness of the tube and that stiffness of the tube leads to deflection depending upon the amount of pressure in the pipeline. Okay. So say you have been using that Bourdon tube pressure gauge for last 5 years. So what will happen? Of course, stiffness is a mechanical property. So because of its multiple expansions and contractions, there may be changes in its stiffness. So say earlier, originally whatever the needle position was pointing corresponding to 0, now it may happen that there may be some shift in the needle position. Okay, but you have not calibrated the device. So in that scenario, what will happen? Every time you are doing measurement, there will be always a fixed bias in the measurement. So that type of error is called as actually biased error or fixed error. Okay. Then third type of error is something. So of course, if you have biased error or fixed error, that can be actually rectified. So that can be rectified with recalibration of the instrument. Okay, or other methods. So you have to identify that what is the reason for that fixed amount of error in your measurement, and then you have to remove that. Third type of error can be random fluctuations. Okay, so of course, whenever you will be doing the experimental measurement, you will not get every time a single value. Say one time you are getting for some parameter, say 72.3. Other time you may get 72.7, 71.8, 70, whatever value actually you are getting. So you will be having some fluctuations in your data. So these are called as actually random fluctuations. And these random fluctuations can be caused because of many reasons. Because of the human error, say you are not able to properly mount the sensor, there is some difficulty in that. So if there is mounting error, then of course that is something which can come as a fixed error also. Okay, but there can be other many interventions which can lead to fluctuations in your experimental measurement. So these type of errors are called as random errors, and many times the sources of the random errors are not known. So when sources of these errors are not known, then we call typically the uncertainties in our measurement. Okay, so uncertainty can be, for example, if you are using a voltmeter for measurement of voltage. So typically whenever you use a instrument, you can take any type of instrument. Every instrument is having some specified uncertainty value with that. Okay, so some instrument is having, say, a range of measurement from, say, 0 to 100 volt. So with that 0 to 100 volt, it might be written that plus minus 2 volt, plus minus 1 volt, plus minus 0.1 volt, or many times it is also written that 0 to 100 volt plus minus 1%. So typically when this percentage is written, it always means that it is nothing but talking about plus minus 1% of the full scale. Okay, so full scale means plus minus 1% of 100. So even if it is used for measurement of 10 volt, with 10 volt I have to use plus minus 1% of 100. How much? 1. Okay. So it means that in 100 it was becoming 1%, but for measurement of 10 volt it has become 10%. 10%. 1 volt uncertainty in 10 volts is nothing but 10%. Okay, so typically whenever this percentage is written in the instrument, it is majority of the time it is of full scale value. Okay, so Now what happens if your instrument which you are using, that is itself telling that it is having uncertainty of say 2 volt or 1% or something. So it means that whatever measurement you are getting out of that, say this instrument is giving me somewhere the value of 10 volt. It does not mean that actual value is 10 volt. It means that actual value can be anything in between 11 volt and 9 volt. There is some uncertainty of plus minus 1 volt in that measurement. Okay. So this is the uncertainty in one variable. Similarly, in my entire system, I can have another variable, another instrument, say for measurement of current, that will be having certain uncertainty. Third variable, I can have say measurement of resistance, fourth measurement of pressure, fifth measurement of temperature. So likewise, I can have a large number of measurements in any system. Okay. So with each measurement, I will be having some amount of uncertainty associated. Now, all these measurements which we have made, say these measurements we are further using in some mathematical relations to calculate some derived variables based on these measurements. For example, if you want to measure power, okay, so for power, what you can do, you have measured the voltage, you have measured the current. Now you can multiply voltage into current. So once you are multiplying the voltage into current, so your voltage and current has become nothing but the independent measurements, and power has become some dependent parameter which is calculated based on the independent measurements. But your if your voltage and current are already having some uncertainty, so of course whatever the final parameter you are calculating based on these measurements, that will also have some uncertainty. Okay, so uncertainty analysis helps us in determining the value of uncertainty of the resultant parameter based on the known uncertainty of the independent measurements which we have made. Is this one clear? So what is the essence of the uncertainty analysis? The essence of the uncertainty analysis is that once we have measured the independent measurements, these are having some amount of uncertainty. Based on these measurements, if we are calculating some output parameter, that output parameter will also be having some uncertainty. Okay, so how much that uncertainty will be there, that is something which we can quantify based on the uncertainty analysis. I think we will not be able to cover this complete today, so we will have one more lecture on this.